Can machines think? This is a question Alan Turing addressed in his 1950 paper, Computing Machinery and Intelligence. And he proposed to ask instead, can machines do what we, as thinking entities, can do? Today we want to talk about the automation of scientific discovery. Turing's question becomes apparent as we wonder if we could build machines that perform tasks that human scientists do. First of all, I would like to give you a conceptual framework to think about that question, and then we will delve into the theoretical considerations. So first of all, what is the condition for automation? The condition is that the machine performs at least as well as the human scientist, and maybe some error is tolerated. So what we wonder about is, what is the set of tasks for which this condition could hold? And we can frame this problem in the context of modeling and simulation. So we think about Albert Einstein, or a human scientist in general, as a system, and we think about tasks as experiments on that system. You can think about the experiment of detecting handwritten digits, or the experiment of answering questions. And we wonder, what is the set of tasks for which we could model the system Albert Einstein to. And if we could model them, then we could automate these tasks, because then we can just simulate them. And if we could model him with respect to all possible experiments, we would speak of a digital twin. But is it even possible to create such a digital twin? And if not, what is the greatest set of experiments for which we could build this model? And let's call this the upper bound Einstein model. So when we think about computability and automation, then the Church-Turing thesis comes to mind, which states that any computable function or algorithm can be performed by a Turing machine. And the Turing machine gets an input, it does some processing or calculation, and returns an output. So it serves as a framework for modeling. And what follows is that every process that is computational, so everything that emerges from computational processes, can be modeled by a Turing machine. And if the computational mind theory holds, then the mind is emerging from computational processes, and we could, in theory, automate everything that has to do with reasoning, because there is a Turing machine that would model exactly that. And then the question is only, can we find our machine that we're searching for? And we can look at the search space, or the space of all possible Turing machines in which all machines lie that could help to automate tasks. And we know that in this space, there will be this upper bound Einstein model. We don't know where, but there will be some upper bound, and it might be the digital twin. So what we need to do is we need to find that model. And in order to do that, we start a search. We want to identify the model that is able to automate specific tasks with respect to the human scientist, or Albert Einstein. So we need a measurement in order to identify the correct model. And what we can do for that is we can just assume that we have everything that Albert Einstein has ever said. So we have perfect data about what he has ever said, and we use that as our measurement method, or as our measurement information, and we perform a model validation to validate the model with respect to these experiments, because we think this might be a good proxy for our digital Einstein twin. So we can then start the search, and when we use a machine to search for a machine, we think about machine learning. This is actually a very abstract description of what machine learning is. And the most easiest approach would be just to enumerate all Turing machines and go through them step by step, and see if the model we are looking at is a model we were searching for, because we already have a defined measurement method. But there we have a problem, because there can be machines that go into an endless loop, and we don't know which go into an endless loop when we try to validate the model or evaluate the Turing machine. And that's known as the halting problem, which means we need to constrain our evaluation time, for example, to 2 hours. But this means we already miss some machines, so we're not able to detect every machine anymore. But even though this puts some limitation on us, we might be still hopeful, and do the search with this constrained evaluation time. And then we find another problem, because there are infinite many Turing machines. And even though we can enumerate them and at some point we would find our right machine, if it's evaluatable in the time we are given, still we only have finite time. And in finite time, we can't search through all possible Turing machines, so there's a problem of finite time and space. So what we need to do is we need to constrain our search space. And the idea behind that is we want the search space to be as small as possible, but still containing our searched for model. So we still want our upper bound Einstein model or digital Einstein twin to be in this search space. And what we do is we use our human intuition to choose a family of functions or family of Turing machines that processes information similar like humans do with respect to certain tasks. For example, when we have an image detection task and we want to classify handwritten digits, we might use the class of convolutional neural networks to search through. And we add some more properties like the amount of pooling layers or whatever it is. But each new property will constrain the search space further. And that's the way we do it. So our takeaway is we need human intuition or human knowledge to be able to constrain our search space. We also might want to have a search that converges to a solution early, not just some search. And for that, we usually use gradient descent in machine learning. Okay, so let's assume we really found the machine where we're searching for, the machine that really models Albert Einstein with respect to all possible verbal experiments with all tasks where he said something. And now we think we solved the problem, right? But then we have another problem. And it is that we have only validated our model on past data. So we can only say this model is validated for Albert Einstein in the past. But we don't know if it will perform well on future questions. So that's the problem of out-of-distribution prediction. And it might be manageable if our data we draw from for our validation and for our inference was IID, so identically and independently distributed. But when we think about future and past, these are two different distributions. And that's a problem. So we can still be hopeful that it might do something useful, but we cannot know. And that's the measurement problem, which tells us that we can only validate models to be able to represent existing knowledge, existing data, so something that's already there. And if we think about automating scientific discovery, we are interested in new understanding and new knowledge. And that's a crucial problem here. So we should rather take them as a source of inspiration, these machines, than as a tool of reliability. Okay, to sum up, I gave you a conceptual framework to think about the question of automation. We talked about the automation condition. I pointed to the theoretical limits, which are limited by the limit of computation in general. So everything that is emerging from computational processes can also be automated. Then we discovered the halting problem and the time and space problem. So that is related to the tractability of search. Are we even able to find the possibly achievable model? And lastly, we have the problem of measurement, where we never have a perfect measurement and we always rely on existing data. So thank you for your attention. I hope that brought some light to this issue, and see you next time.